Hello. 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 Hello, Dr. Rabindran.
Hello, sir.
Hello, Dr. Rabindran. Good afternoon. Good afternoon.
So, can you hear me?
Yeah, I can hear you. I can.
Okay.
Good afternoon to one and all. Can you hear me?
Yes, sir.
Yeah. We wholeheartedly welcome all the participants today for this international webinar on porous solid zeolites in petroleum refining and biomedical applications, to be delivered by Dr. Rabindran Jami, Assistant Professor, Department of Nanomedicine, Institute for Research and Medical Consultations, Imam Abdul Rahman bin Faisal University, Dammam, Kingdom of Saudi Arabia. I welcome you, Dr. Rabindran, for this international webinar as resource person.
Thank you.
I also thankful to the convener, Dr. A.R. Sasikumar, Assistant Professor, Department of Chemistry of Vinaya Mission Engineering College, and Dr. M. Tamilvanan, Department of Chemistry Assistant Professor from the same institution, as well as the President of Institution's Innovation Council, Dr. Arun Kumar Madhavapan, as well as Dr. Sendil Kumar, Head of the Department of Physics, for this wonderful arrangement of this international webinar. I hope all the biomedical as well as biotechnology students will be enriching their knowledge through this international webinar. The topic is highlight the need of the hour today, and I am very much thankful to the resource person for accepting our invitation to deliver the international webinar. I am handing over the proceedings to the convener for further progress. Thank you.
Thank you, sir. Thank you for your very kind words. Before going into the presentation, I would like to give you a short bio about the research person. Dr. Rabindran Jermi is an assistant professor at Institute for Research and Medical Consultation, Imam Abdul Rahman bin Faisal University, Kingdom of Saudi Arabia. Dr. Rabindran has obtained his PhD degree in chemistry from Anna University, India in 2006. Dr. Rabindran has been active in nanomaterial design research for more than a decade. At Imam Abdul Rahman bin Faisal University, he is involved in developing hierarchical aluminosilicates using mesotemplate cetyl trimethyl ammonium bromide and desilication technique for drug absorption and release study. Functional is external port channels with different silane functional groups such as 3-aminopropyl triethoxysilane and 3-chloropropyl trimethoxysilane. Increase biocompatible of the system by wrapping with linear polysaccharide cytosine and polylacticoglycolic acid. Steady controlled release and targeted delivery of drugs, dual functionality with respect to tumor imaging and drug delivery. Dr. Rabindran had been a research scientist at King Fahd University of Petroleum and Minerals, Dahran, Saudi Arabia for 8 years, and as a postdoctoral fellow at Busan National University, South Korea for 2 years. During this tenure, his contributions in the field of nano-based zeolite preparation and petrochemicals are of great significance, which addresses the developing commercial technologies in collaboration with leading chemical company like Honeywell Company USA, Saudi Aramco Saudi Arabia, and collaborated with the Japan Cooperation Center JCCP Japan. During his association with UUP, he was involved in the selective conversion of low-value petroleum-derived feedstocks such as toluene and methanol into high-value petrochemicals product paraxylene production utilizing nanozeolite-based catalytic method. He has managed a long-term ongoing project on consulting and technical services to refineries and petrochemical industries. He has been very actively involved in joint Saudi-Japanese research program on high-performance catalyst development for dehydrogenation. Dr. Rabindran has contributed in the catalyst development of hierarchical nanoparticles NIO, alpha beta B2O3 and gamma L2O3, alumina-based nanocatalyst system for oxidative dehydrogenation of N-butane to butadiene in collaboration with Prof. Asoka Japan Cooperation Center, Petroleum, Core PRP. Dr. Rabindran has been very active in patenting the novel research that he has conducted in the area of petrochemicals and petroleum and has 2 patents granted, 6 patents filed from United States Patent and Trademark Office. Dr. Rabindran has published 64 papers in WOS journals and his H index is of 23. He has presented several research papers in national and international conferences and workshops. His research work has been widely cited with total citations of 1,456 in scientific literature and technical reports. Okay, now I would like to hand over the stage to Dr. Rabindran Jermi. Jermi, now the stage is yours.
Thank you, Dr. Tamilvan, for the brief introduction. I hope I am audible to you all.
Yes, we are audible.
So I will share my screen. So as it has been told, I will discuss about the porous zeolite in petrochemical refining and biomedical application. So I am working in the medicine research, but I can echo is there once again. Hello. Is it possible to mute?
Yes, Dr. Rabindran Jami, we are hearing your voice. It's audible to us.
So you're able to see my screen?
No, we are not able to see your screen.
Okay.
Dr. Jeremy?
Yes.
We could not hear, sorry, we could not see your screen.
One second.
Our screen.
Hello, sir. Jeremy, sir. This is Arun. Hello, sir. Can you hear me? Hello, Jeremy, sir. Hello. Hello, Jeremy, sir. Sir, this is Arun. I'm.
Yes, sir.
Sir,
Sir.
you go to that arrow mark, sir. You first stop sharing now. You press the cross mark there. Now you go to this arrow mark.
Yes, I meant.
It will be showing at the bottom PowerPoint presentation like that. No, before that you make your PowerPoint presentation available in your desktop, desktop of your desktop.
Yeah. Yes, it's
and
available.
open that PowerPoint presentation.
Okay.
First open it, and now you go to this arrow mark.
Okay.
Then you can see that PowerPoint presentation at the bottom.
Yes. Okay. Thank you.
Now you can share, but don't put in a presentation mode, sir. It won't work.
Okay.
Now you move the slide. Next slide, sir.
Okay.
Have you moved? Next slide.
Yeah, I moved.
But it won't. Okay, sir. Now it is okay.
Okay. Okay.
Okay, sir.
Thank you.
Okay, sir.
So this is sir, excuse me. This is the overview. I'm just going to give introduction about zeoporous solids. How about the market consideration, synthesis and characterization, petrochemical applications like fluid catalytic cracking, transalkylation, alkylation, and oxidative dehydrogenation. And I will touch about the biomedical application, opportunities and conclusion. So as you know, the zeolites has traditionally used long time, even before 2000 centuries. 2000 years back. It is used as a water decontamination. For example, heavy metal adsorption. And also it is used for the construction, agriculture, and petrochemistry. So the structure is basically made up of steel and aluminum atom, and then it forms a secondary building unit, and it has a 3D structure. The texture and pore can be modified by different techniques. As we can see in this slide, there is a pure silica zeolite. This can be modified with isomorphic substitution, and also the alkali modification will give the basic characters. And it can also be a bifunctional catalyst. So in the right side, you can see the different particle size will change into nanozeolite, hierarchical zeolite, and 2D zeolites. So So like this, we can change the texture and pore size of the zeolites. So in today, there is more interest in the petrochemical about the oil to chemical perspective. Okay, so usually we have been used for fuel transportation sectors, but now as you can see that the petrochemical global growth projected at 4% per year compared to 0.8% per year. So there is also a pressure, okay, of not using petrochemicals and in the as it increases the pollution levels. So there is a drive towards electric drive vehicles. So the industries are now want to utilize these petrols to change into chemicals. Okay. And it is also used in different companies like textiles, and so we can modify its properties, okay, and apply in the different applications as I'm going to show you. So these are some of the special chemicals that can be synthesized selectively from the crude oil gas. Okay. For example, ethylene, propylene, butane, and they call it BTX, the benzene, toluene, and xylene, and methanol. Okay, so this is the market trend. Okay, so you can see the fuel demand. It is at the bottom, and there is significant demand for petrochemicals and natural gas demand. So we have to use this as such a market consideration to do our research. So, for example, I'm giving here the Grace company's process for petrochemical. You can see here there is the process they are utilizing: FCC, cracker, and on-purpose routes. So in the feedstock, you can see that when you get the vacuum gas oil, they will treat using Y zeolite matrix, and it will crack the petrochemical product into FCC gasoline, and there is also low yield of LGP. And further, it will be cracked using ZSM5 zeolite. It is the small pore zeolite that will give you propylene, butylene, and also increase octane of FCC gasoline. So this is a usual process in the company. Okay, so it depends on the market trend. Usually the petroleum, we use FCC, propane dehydrogenation, and steam cracker. And usually it is dominated by North America, and followed by Latin America, and then the East Asia. So we develop a hierarchical zeolite. It is different from the conventional zeolites. In case of the pores, okay, conventional zeolites are micropores, while it is of micro and mesopores, and also the acidity will change. So we are going to see about the 4 types of process: the fluid catalytic cracking, transalkylation, alkylation, in particular toluene methylation, and oxidative dehydrogenation. So the catalyst they use is a mixture of catalysts. It composed of white zeolite and ZSM5. So the white zeolite, it will crack the petrochemical product in fuel gas, LPG, naphtha, and LCO, SCO, and CO. And they will add small micropore ZSM5 as additive. So it will further selectively give propylene and butylene olefins. So this is a conventional form. So here we are going to try our hierarchical zeolite. These are the different techniques to create hierarchical pores, like demethylation, templating, recrystallization, and deposition technique. So here I'm going to show you, we used the templating technique, like acetyl trimethyl ammonium bromide, okay, and then alkaline condition, micro and mesopores. So this is the development process. We use a power reactor to synthesize the zeolites. So here you can see that the heat has been homogeneously will be maintained, and inside we will add all the ingredients. As you can see the scheme, we use a silicate precursor, and then we do hydrothermal treating, and in alkaline condition we add acetyl trimethyl ammonium bromide, and then we and micropores. So the FCC catalyst component consists of following things, like binder, clay, and the white zeolite, and alumina. So these are the combinations, and ZSM5 additive. So here you can see that, so it will be initially in the powder form. Then we will mix all this together and we form a extrudate. Okay, so it will be uniform particle size. Like then we will sieve it between 0.5 to 1 mm. So this way we can avoid the non-reproducibility. So always we have to use in the pellet form. And also, while revealing the detail of the catalyst preparation, you have to give the range, like gel composition. So here we can see that, for example, in the case of SPA16 preparation, we have to always calculate the gel composition. So I'm giving you just an idea. If you are a new starter, so you have to always reveal the detail in gel composition. For example, if you take a 24 gram of silica, we have to change into the mole, and then overall we have to divide by the silica content. So this is the gel composition in the equation 2. Okay. So this is the research note we usually use. While you are patenting also, they will require such research note. So it will consist of the project number and date and one of your colleagues' signature. Okay, so you always have to enter. Each day you enter into the lab, you have to maintain specific research note. Okay. So these are the characterization I'm going to show you about the hierarchical zeolite. We used X-ray diffraction, nitrogen absorption, aluminum NMR, and transmission electron microscope. So in the XRD, we can see that the conventional catalyst like ZSM5, aluminum MCM41, it is in single phase. So when we generate the hierarchical zeolite, both nature will combine together. We can see that there is a meso and micropore. We can also tune the amount of mesopore and micropore. Sometimes, if your alkaline treatment is not enough, you will get disordered hexagonal also. So we have to be careful in choosing the alkaline condition and synthesis condition. This is the surface area measurement analysis. Here we can see that the presence of dual pores, while there is a single pore in case of mesopore or micropore zeolite. So this is somewhat unique texture property of hierarchical zeolites. Also in aluminum NMR, which describe you about the aluminum coordination in the framework. So usually the zeolite will have bronzer acid size. Because we treat with the alkaline condition, its nature changes. More of octahedral and tetrahedral coordination observed. So the chemical environment of the active site changes in case of this composite zeolite. Similarly, in the FTAR, we can see is the MCM41. It is the mesopores, and beta is the zeolite. But hierarchical beta, it will have a unique peak between both the meso and micro. So it has the property of both zeolite and mesoporous zeolite. Similarly, different type of beta zeolite or Y zeolite, their composite can be prepared. This is the transmission electron microscope. Here we can see that the conventional MCM41, it is a mesopause. It will have unique mesopause. But here you can see that once the composite forms, there is two types of phase. There is a disordered phase that is due to presence of nanozeolites in the mesopause. So the textural nature changes. And we measure the acid characteristics, the acidity. You didn't absorb the FTR and ammonia TPD. The ammonia TPD will give you the total acidity, while in FTR will give you about the Bronsted and Lewis size. So here we can see similarly intermediate Bronsted acid size presence. This is a pictorial representation. We can see that the moderate and weak acid size remains, while there is a significant reduction in the strong acid size with modification. So This is a fluid catalytic. Here we normally use 2 to 5 gram of catalyst, and the feed of a VGO 1 gram. Okay. We will maintain the catalyst to oil ratio from 2 to 5, and WHSV 16. Okay. So we always measure at the constant conversion level. It is around 75% at 520 degrees Celsius. As indicated here, we can see that the market relevant propylene and the ethylene to propylene, it all increases with the composite formation, as you can see. So this is very important, as the composite increase the valuable products. This is another reaction, the transalkylation. Here you can see that there are is going on, like transalkylation, isomerization, disproportionation. So we have to choose a particular zeolite. We have to tune the acid and basic characters. Okay. So this reaction was carried out in the BTRS junior reactor. So here you can see that we pack the catalyst inside the reactor. So it will be around 1 gram of the catalyst. Okay. The feed will come from the top, and then it will enter to the reactor and then pass through the online GC. So the GC has different columns. It measures the gas phase, liquid phase. So the design of zeolite, it will have a beta zeolite. We made it desilication using a 0.1 to 0.4 mMols sodium hydroxide, and we generated the meso and disordered pores. So such material was then loaded with molybdenum active site. So here you can see the xylene yield. Okay. It increases with the composite catalyst. Okay. So here 4 reactions are carried out. Dealkylation will occur, transalkylation, disproportionation, and pairing reaction. So we have to choose a particular active metal that increase the xylenes. We also run the toluene methylation in combination with the UOP. So we use the pilot plant. It is called a P3401 for a toluene alkylation for methanol to paraxylene. So it also has so many other side products. So toluene react with methanol to give xylenes, and then also sequential methylation occurs, MTO, and alkylation occurs. Here we selectively target the paraxylene because that is commercially valuable product. And we set a technical target to improve the toluene conversion, the paraxylene, and reduce the selectivity to benzene xylene. Okay. So for example, we compare with the SABIC unit and a mobile. So we set a target. So this is a modification, core modification we have to do on the zeolite to increase the parasite. They particularly deposit the selenol on the external surface of the zeolite. So it will reduce the pore size and it will lead more the para product. The ortho and meta product will be restricted. So in this way, we develop a series of catalysts using chemical deposition technique. Here we can see that we reflex with the X-ray at 70 degrees Celsius and we calcine 5 to deposit the silica on the zeolites. So this process can be repeated 1 to 5 times to increase the selectivity of the paraxylene. So here we can see that compared to ZS5 zeolite, we are able to increase the methylation. Okay, that will give more the commercially available xylenes. And also we reduce the disproportionation reaction. So here we can see that the xylene selectivity increases while the trimethylbenzene selectivity decreases with catalyst modification. We compare around 10% conversion. Similarly here, to conversion level, we compare 4 different catalysts. Here also, the presence of silica as a nanoparticle on the hierarchical zeolite is increase the paraselectivity. So like this, we choose the best combination of the nano formulation. And we do different cycle of TOS coating, like 1x, 2x, 3x, as goes on up to 6x. You can see that we can increase the paraxylene to total xylene ratio. More importantly, the conversion of toluene and methylation remain constant. So these are some of the packing catalyst detail in the pilot scale instrument I want to show you. So we can see we have to always take all the detail into the consideration. So in the diameter, so how to pack the quartz wool at what centimeter, and how much catalyst and diluent we use. Okay, 3 centimeter, and the quartz wool again we will keep, and then the diluent is silicon carbide, and again we pack with quartz wool. So this is the way we have to always pack to reproduce the experimental procedure. So this is the final packing of the catalyst. Okay. The first will be quartz wool, second will be the catalyst, diluent, quartz wool, diluent, again quartz wool. So this is a feed mixing. Here you can see that we take toluene and methanol and 2 separate vessels, and then we mix together, okay, and we put in the feed. Okay. So here you can see that this is the activity for over 100 hours of steam. You can see that the stable activity of the catalyst the para-xylene to total xylene ratio. The blue color, it increases with increasing the ratio. And also there was several zeolite combinations were tested, and we see the stability of the catalyst has to be remain constant. So prior to this study, we will also study the empty reactors, and also we will pass only reactant, and we see what are the cracking product occurs. This is the another oxidative dehydrogenation process where we convert valuable butane to butadiene. Okay, so it has been extensively used in the for the preparation of tires, etc. Okay. But this process is endothermic process, and also there is so much coke formation occurs. So we have to use a different technique to reduce the coke, reduce the energy. So we normally use oxidative dehydrogenation process, in which we pass the oxygen in presence of butane, so it will change to butadiene, and side product will be water. There are other two processes are there where they can use mixture of olefins like butenes and ethylene. In another case, we can use the carbon dioxide as a oxidant. So this is the recent trend where we can utilize the low valuable carbon dioxide as a oxidant. So this is a thermodynamic equilibrium of N-butane dehydrogenation. You can see here it is thermodynamically controlled. The butadiene phase form above 550 degrees Celsius. There are other products like 1-butane, cis-2-butane, trans-2-butane. The different loading of nickel on gamma alumina catalyst was studied between 400 to 500. So this is a trend we observe. We can see here that by changing the nickel content between 0 to 30, we can increase the butadiene selectivity. There is also other products like partial oxidation, cracking, and C4 beams. In this process, the influence of bismuth was studied after optimizing the nickel content on the gamma alumina. Here we can see that still we can improve the butadiene further, and we can completely reduce the side products like partial oxidation and also cracking. So this is the overall mechanistic work. Here you can see the bismuth act as a effective oxygen transmitter to the nickel, which is in green color, that help to supply the oxygen selectively to increase the butene, and it will further undergo oxidation to butadiene. And we found that the calcination step, that is very important. And we compare here the one-step calcination to two-step calcination process. Here we can see that the butadiene selectivity increases from 18 to 40, and also the partial oxidation and oxidative products decrease considerably. So we can study similarly the effect of calcination. So the active site of the nickel play a major role. And also we used 3 other different catalysts made up of silica gel, formed silica, and silica salt. Here we can see that we can further improve the butadiene product up to 51%. So this silica effectively acts as a bismuth nickel oxide cohabitation. So here we can see that in silica gel it forms the large particle. Okay. But here in formed silica, we can see that the effective mixture of active site occurs. The nickel bismuth, and then it sits on the pores of the silica. So this is some of the petrochemical applications, and here we can see that the biomedical. In previous section, the silica to alumina ratio was between 23 to 18. But here you can see that we can reduce the ratio of aluminum, okay, which is maybe little bit. So we vary the aluminum content between 280 to 2000. So a little modification we can apply in the biomedical application. So it can act as a very good antioxidant carrier, and we can use in cancer therapeutic. So in present situation, there are a lot of research going on the development of drug delivery. So what is the difference? Here you can see that in case of tumor, the classic delivery, it involves the passage of drug in non-selective manner. It can also reach the cancer cell and also the normal cell. So it will affect both the cancer and normal cell. So in case of nanomedicine delivery, we can see that we can selectively target the tumor. And also we can reduce the toxicity and improve the damage occurs to the other organs. So these are the different way, like injection, pulmonary, oral, systematic, transdermal patch, where it occurs. So here we can see the nanocarrier drug delivery market is showing a positive sign, and it has a lot of opportunity to work on this phase of research. So a perfect drug delivery system need to release the drug in a sustained manner, and it can also be like a smart, it can open and close based on the requirements. So these are some of the targets which we go as close as possible. And here you can see that different components like drug A, drug B, and also the pH, temperature, redox, enzyme activity, proteins, we can functionalize. We can also go with the different polymers like polyethylene glycol, chitosan, like that. Because the presence of large surface area, the nanocarrier can accommodate all the functional groups. It can be a good drug delivery system. So these are the different type of porous solids that has been used recently, like carbon nanotube, dendrimers, micelles, liposome, quantum dots, and sympions. Sympions gold are used for different imaging purposes. So it can be used as a multifunctional. Okay. So what are the advantages? It is stable against biochemical and bioerosion, and it can load drug, and also we can see that we can control the amount of drug and other components. So this is the basic concept for drug delivery study. Here we can see that we use some of the drugs. It can be any drug. We can load on the nanocarrier, and then we can see the release study at different pH. The pH condition can be based on the cancer condition. Okay. It can be pH 2 or it can be pH 5.6. It depends on the type of cancer you want to study. And we see how much drug has released, and we can use UV visible absorption spectroscope or HPLC to measure the drug release. These are the techniques used. We can use the dialysis membrane technique, which is very simple, where we can use the beaker and the dialysis membrane. Inside we can put the nanomaterial, and we can see the release at different pH. The nanomaterial can be designed in different ways, and we can study which one is the best nanoformulation. So we normally use the Permagear system. Here we can study up to 8 nanoformulation in a single stretch. It consists of the receptor reservoir, where we can put the pH of the solution, and here in distribution manifold, it is the Frank cell. It will mimic the human body condition. It will have a membrane and the drug. So we will put the drug on the top, and then we pass the PBS solution. So the drug will pass through the cell, Frank cell. So what are the advantages? Here you can see that the A corresponds to the cancer drug. It's a cisplatin. It is a crystalline material. So the C corresponds to the nanocarrier. So if we mix both together, we form a amorphous transformation. The nanocarrier helps to change the crystalline form of a into nanoform. So what are the advantages? Here it will increase the solubility of the drug and biocompatibility. So this is very important, that it will increase the drug reaching to the site. So we can see here there is a combinational herbal drug like tridam, which consists of active component gallic acid. So we try to load a different concentration, like ranging from up to 20 millimole per gram of support. And we see how effective it will change the crystalline to nanoform. Here we can see that the cargo, the nano vehicle, on the top, the antioxidant is there. So, but in mesosilicate, which is the effective nanocarrier, we couldn't see such crystalline gallic acid. So this very good important highlight about the hierarchical silicon. This is another where we use three types of antioxidant, like ascorbic acid, curcumin, and coenzyme Q10. This coenzyme Q10 are not stable, okay? It easily disintegrate, and also similarly curcumin. But we can improve the stability of the antioxidant, and we can able to absorb the large antioxidant based on the different silica to alumina ratio. We found that around 8, we are able to absorb the maximum. In this case, we loaded cisplatin and studied the drug delivery study. You can see that it is able to release in a sustained manner compared to other nano formula. And here we can see that based on the application, we can use any formulation. The one which is releasing very slow, it's not bad, but it releases sustained manner. Whenever we need a slow release of the drug, we can use this combination. In case if we need very fast release, we can use the mesosilical ion. So like that is based on the application. We can also study the effect of solvents, like when we use DMSO while forming the nanoformulation, we observe that more of a aggregation occurs. But when we use the normal saline solution, this dispersed drug occurs, and it was very active against the mammary carcinoma and cervical cancer.
Excuse me, Dr. Jeremy.
Yes.
Sorry to disturb you, but actually we could not see, your slide is not changing.
Can you say?
No, it remains in the same slide. So it is from development of drug delivery system. It is about advantages.
Okay, now.
Dr. Jeremy? Yeah, it's visible now. It is visible.
So I want to repeat or
No, it's okay.
okay. So in this slide, you can see that the magnetic sympionts are impregnated on the sps16 for cisplatin delivery. Here you can see that the presence of cubic shaped silica has more advantages compared to other nano formulation, and it presents high surface area lead to effective functionalization of aminopropyl silanes and biocompatible polymers like polyacrylic acid. And we are able to load cisplatin and study the anticancer activity on colon, cervical, and normal cells. Here you can see that the Urch staining, which used to identify the living cell, the dead cell. You can see after treated, the cells are dead. So it shows the effective nanoformulation that can penetrate into the cancer cells. This is another type of magnetic spinel ferrite silica composite that has been used for cisplatin delivery. Here you can see that this type of magnetic nanoparticle are very cheap but effective. So the spherical silica are uniform in size, around 80 nanometer. It will increase the heterogeneity. So here we loaded copper spinel and we generate the magnetic property and we load cisplatin. It was very effective. It doesn't induce any toxic effect on the normal cells. And here you can see that we similarly developed other type of spinels like nickel, cobalt, and manganese spinel ferrite. And then we wrap with biocompatible polymers like chitosan. Here what we observe is in this wrapping procedure, there is a pH adjustment process. But during that time, the drug seems to come out of the pore. So we optimize and we wrap the polymer one step ahead. Then we loaded the cancer drug. So in the method 2, we can see that it has very good anti-cancer activity. But if you go on the method 1, we couldn't see any inhibitory effect. So there is need to be optimization. Okay? Here you can see that in the first method, there is a control and copper, spinel loaded silica, and cisplatin. Here you can see that the red color cisplatin is very effective compared to our nanoformulation prepared by method 1. But however, if we change to method 2, here we can see the activity close to the standard drug.
There may be some impurity or something else because when they are slowly used, we see is separately.
So here we can see that this is the MCF7 cell examined by transmission electron microscope. We use the ultramicrotomy technique where we, after loading the nanoparticle in the cells, there is some treatment, and then we trim and we section by ultramicrotomy, and then we absorb. So this is the MCF7 cell in the first cell. Here you can see that the compact nature of cells, with the nucleolus, nuclei, and then it is surrounded by the cell membrane. So in the right side, we can see that there is a complete damage occurs, and there is a penetration of the nanoparticle into the cells. So this shows that our nanoformulation effectively enter into the cell. Similarly here, the Hodges staining. Here we can see the cisplatin loaded drug. It is in the red color. Okay, it entered into the cell. Okay. So this confirms the effective nanoformulation. So I will also touch some of the prospect. We can work based on the current situation. We can develop a pulmonary drug delivery system. Okay. But there are some challenges there, as lung is a unique organ. So we need to make a formulation that bypass the different metabolism. For example, here you see that our drug delivery carrier can help the drug concentration at the disease site. So the present pandemic situation, we can develop a nanoform, but there are some requirements. The nanocarrier needs to be the size between 10 to 200 nanometers. So this is the one shown to enter the lungs. Okay. Different size of nanoparticles are there. 1 to 5 micrometer deposit in the deep lung, while 10 micrometer deposit in oropharyngeal region. However, the 200 nanometer to cross the cellular barrier. So while designing the drug, we have to take all this into consideration. So for example, here you can see the different type of drugs. The combination drug are effective for COVID-19 patients. So similarly, we can design a nanoparticle. We can keep intact some of the drugs, and we can coat with a biocompatible polymer. For example, here MD-SWA, hydroxychloroquine, and combination like favipiravir. So these are some of the ideas I like to give, so that we can involve in the upcoming research. So I like to conclude here. So we saw about the synthesis characterization of hierarchical zeolite, how the silica-alumina ratio can play a role both in petrochemical and biomedical application. So there is a interdisciplinary field of approach needed between chemistry, biology, and physics. And I also thank to collaborators like Center for Petroleum Refining and the Saudi Aramco, and some of the researchers from our university are different departments. Thank you.
Thank you very much, Dr. Rabindran Jermi, for your excellent presentation. Dr. Rabindran Jermi, on behalf of everyone here today, we thank you for taking the time to speak with us today on the very important, interesting research topic. And we are sure your presentation would provide more information for the research and student community. Dr. Jermi?
Yes.
Actually, I have a doubt from your presentation.
Yes.
So I have noticed in one of your slides that you have used ALNMR for characterization for zeolite, I think so.
Yes.
So is it soluble in any solvent?
This is a solid state NMR.
So this is from solid state NMR.
Yes, solid state.
Oh, okay, okay. Okay, now I request the participants to raise your hands if they have any doubt to clarify with our resource person.
So one more question. Can we use zeolite catalyst in conversion of alcohol directly into gasoline?
Pardon?
Can we use zeolite catalyst used in conversion of alcohol directly into gasoline?
So it's like biofuel. I'm sure we can use it.
Okay.
Yeah, I'm sure.
I request the participants to raise your hands if you need to clarify any of your doubts. So there's no doubt from audience. So I request Dr. Somanathan to clarify his doubt. Dr. Somanathan, can you please unmute your mic?
Yeah, first of all, I would like to thank the organizer to organize this international webinar. And the resource person, Dr. Rabindra Janni, you have given a very good lecture about the porous material and that porous material in various application in various fields. Okay, I would like to have one suggestion and one question. Whether this silica, as we have discussed about the spherical silica nanoparticle, whether this spherical silica nanoparticle will play a vital role in against the treatment of COVID-19? Whether it is possibility.
Because the spherical nanoparticle, as I said, it has around 80 nanometer size. So from 10 to 200 nanometer are effective for such study. So it will be definitely useful.
But this material, whether you are going to make it as any drug like a carrier, this silicon nanoparticle will act as a carrier, or you are going to use as any instrumentation for sensing the viral particle, because nowadays the viral reflection will be there. Okay, always it is double now. So how this material will perform, whether as a drug or any like making a mask or any filter or in any instrumentation for sensor like that, this material will be useful?
Yes,
Or directly we can use as a drug vaccine?
it can be used in first case as an effective nanocarrier. Like we
Okay.
can load some of the drugs which are active, and we can coat with biocompatible polymers, and we can use either like a powder, okay, like a spray drying technique, or we can also use as a tablet form. So these are on the research study.
Okay.
We can use it, and also we can use as a immunoassay technique where it can detect such a viral particles. We can use. There are so many applications. You can use it.
Okay. Okay. Thank you. Once again, I thank you to the organizer to organize this nice webinar, international webinar, and also I thank to the resource person, Dr. Rabindra Jani.
Thank you.
Thank you, Dr. Somnathan, for your discussion. I request all the participants to fill the feedback form that I have posted in the chat box, and you can download your certificates. And now I request Professor Gilbert Raj to deliver his vote of thanks for this trip.
Good evening to all. I would like to thank our chief guest, Dr. Rabindran Jarmi from Imam Abdul Rahman bin Faisal University, Kingdom of Saudi Arabia, for his wonderful presentation on porous solid zeolites in petroleum refining and biomedical application, and enlightening us with his knowledge. Today's webinar was full of knowledge and interesting things. It gave deep insights into the zeolites in the petrochemical and biomedical application, and also revealed some interesting facts. I would also thank our beloved principal, Dr. A. Nagappan, for his valuable guidance and moral support. I am happy to express a vote of thanks to our HODs, faculty members, students, and participants from various institutions that have made this webinar a grand success through their motivation and dedication. And a great thanks to everyone. And with this, we shall conclude our session. Thank you. So I request you to give your feedback and get your certificate.
Thank you, sir.